Alright, thanks for coming, and today, by popular demand, I will solve an equation that is quite fishy, namely Poisson's equation. And you'll see there's quite a bit of analysis involved, but it's really cool analysis, and in my opinion, it shows you why analysis is useful. So let me not spoil the surprise, let me start with that. So what's our goal? Is to solve the equation minus Laplacian of u equals to f. And this is what's called Poisson's equation, and f, it's given, and more importantly, it's as smooth as we want. We can differentiate it as many times as we want, even though in practice we'll just do it twice. And of what's called compact support. All that it means, it's really infinity. It's zero when x is very big. So when you integrate by parts, you don't really have to worry about boundary terms. So a typical function f might look like that, something like that, like a bump function. And how do we solve this? Well, the only thing that's given that we know is Laplace's equation. So Laplacian of u equals to 0. And in a previous video, I told you that one solution of Laplace's equation is given by this fundamental solution. So let me just recall this. Well, phi of x, fundamental, solves Laplace's equation, and it's given by 1 over n times n minus 2 alpha n, where alpha n is just the volume of the ball in Rn. So it's the volume of one B0, 1 in Rn. And this times 1 over x to the n minus 2. In absolute value. So this is a fundamental solution, and one thing that we've learned before is that it solves Laplacian of phi equals to 0. And the question is, from this, how can we build up a solution of Poisson's equation? Well, all you do is multiply this phi with this f. But here we don't want to multiply it algebraically. We don't want to say f times phi. We want to multiply it in an analysis way. And by this I mean the convolution. So claim if we let u of x to be phi times f, so phi convolved with f of x, which is just the integral of Rn of phi of x minus y, f of y dy. I'm claiming that this solves Poisson's equation minus Laplacian of u equals to f. Okay, and we will prove this. It'll take quite a while, and I skip a bunch of steps. But as I said, enjoy the ride, it's very exciting. And as I also said, it'll involve quite a bit of analysis, and let me show you why. Suppose, okay, you're someone who's like, I don't care about analysis, let's just differentiate under the integral, because why not? Analysis is useless, right? Let me show you that it's actually pretty useful. Because suppose you took Laplacian of this. Step 0. Suppose, let's do a wrong calculation. Let's say calculate Laplacian of u, which becomes Laplacian of this whole integral of phi of x minus y, f of y, dy, and suppose I put, why not, the Laplacian inside, because I don't care, I can do whatever I want. So you get Laplacian of phi of x minus y times f of y dy. But hey, I just showed, in a previous video that this is 0. So in fact, this becomes 0. So yet, in fact, the Laplacian of u equals to 0. Whoa, okay. Not again. Wrong! So wrong, I broke the chalk twice, okay? Why is this wrong? Because analysis is useful. If you didn't care about analysis, you would clearly make a mistake because Laplacian of u is not equal to 0. And you may ask, what went wrong? Precisely what went wrong is that this term, and remember, phi of x is 1 over xl to the n minus 2 times some constants. This thing has a singularity at 0. So it blows up at 0, which means that it's very badly behaved. And in particular, because of this ill behavior, we cannot simply put the derivative inside the integral. So we have to be very careful, or in math we say, we have to use analysis. All right, step 1, let's pull out of math revolvers and let epsilon be positive. So epsilon be positive. And again, that's because we want to isolate stuff near 0. Okay, now if you remember, we did a very bad thing. We differentiated under the integral. It was bad because phi has a singularity. That said, there's another thing we didn't really talk about, namely f. F is actually very smooth. And because f is smooth, this actually allows us to put all the derivatives on the f. So, in other words, it's okay to say that Laplacian of u is equal to Laplacian of integral over Rn of phi of y f of x minus y dy. And by the way, I got this formulation from a change of variables. So if you let z equals to x minus y, you can actually get z minus y here, I believe. Okay, so we get this formulation, and as I said, it's bad to put the derivatives on the phi, but it turns out, because f is smooth enough, it's actually okay to put the derivatives on the f. So in fact, it is legit to say that this is phi of y, Laplacian, I guess with respect to x, of f of x minus y dy. And I did skip a big step because otherwise this video is 2 hours long, but if you want to justify this rigorously, one thing you can do is replace the derivatives by limits. The derivative is just the limit of slopes of secant lines, and then what's called the dominated convergence theorem, which allows us to put limits inside the integrals. So just trust me, it is legit, I do want to move on to more exciting stuff. Okay, and now, as I said many times, phi has a singularity at 0, so what we're going to do now is isolate the singularity. So here we're actual doctors, medical doctors, and we're going to do a surgery. So suppose you found a mole at 0, the way you do surgery, you isolate the mole, and then you just take it out, okay? So in fact, because phi has a singularity, let's split up this integral to a term around 0 and a term far away from 0. So in fact, you can write this integral as the integral around 0 of phi of y Laplacian of f of x minus y dy, again Laplacian with respect to x, plus a term that's far away from 0, Rn minus b of 0 epsilon of phi of y Laplacian of f of x minus 1 dy. And those are two terms, okay, a and b, and we're basically going to study this. But again, just as an illustration, 0 is the point where things are bad. So what we're going to do is, we're first going to focus on what's happening around 0, and then we're going to focus on what's happening far away from 0. And here's our game plan. We're actually going to show that around 0, phi, despite its singularity, is not that bad. And we'll also show that far away from 0, that's surprisingly where all the interesting info is. Okay, step 2. Study of A. Let me remind you what A is. And by the way, we want to show that A goes to 0, so let's estimate the absolute value. So what this is absolute value around 0 of phi of y Laplacian with respect to x of f of x minus y dy. Now, there is the triangle inequality, which tells us we can put the absolute value inside the integral. Which makes me think analysis is really the study of putting stuff inside the integral. Okay? It's like a suitcase. Okay? So in fact, this is less than or equal to the absolute value of phi of y, absolute value of f of x minus 1 dy. Okay, and now remember that f is smooth. Not only it's smooth, it has compact support. So far away from 0, it's actually not too bad. In particular, what I'm saying is that f and all its derivatives are actually bounded. So f attains a maximum, df attains a maximum, and so does, the second derivative. In particular, I'm telling you not to worry about this term because it is bounded. So this thing is less than or equal to some constant that we don't really care about. So in the end, what we're left with, this is less than or equal to constant integral around 0 of phi of y dy. And phi is positive, so we can remove the absolute value. Now, in theory, this term could be very bad because remember, as I said 20,000 times, phi has a singularity around 0. So it's definitely possible that this integral blows up. That said, I will show you that precisely because of the exponent of phi, this n minus 2, we're actually lucky and the integral does not explode. So it's like a bomb that we're scared of exploding, and in the end it didn't explode, so it's good. All right. But for this, we actually have to calculate this integral, and because phi is radial, what would be nice is if we had some kind of a polar coordinate formula, which in fact we do. So fact 1, I call this it's called the coarea formula, or the polar coordinate formula, or what I like to call the onion formula. And you'll see why. What this formula tells you is that, just like an onion, you can decompose this ball of radius epsilon in terms of smaller balls. So if this is 0 and this is epsilon, think of this ball as being decomposed of smaller rings, like onions, and suppose the typical ring has radius r. What this tells you is, instead of integrating this function from 0 over the whole ball of radius epsilon, what you could do is integrate this function over a ball of radius r, and then integrate r from 0 to epsilon. So what this equals to is integral from 0 to epsilon of something dr. And what you put in this dr, it's simply you integrate the function over the sphere radius r. So it really just becomes like that. Integral from 0 to epsilon, integral of sphere b0r of the same function, phi of y, times the surface measure of that ball. So think of your thetas or something. So d sigma of y. And this is a very important formula, and I might mention it more and more in the next couple of talks because it is, as I said, it's very useful. So in some sense, it is like the polar coordinates formula because r is the radius. So we're integrating from 0 to epsilon. And then theta is the angle. And you might say, where does the r appear? Well, it's precisely in this sigma, in the surface measure. All right. So we have that. And once we have that, it turns out that it's easier to integrate this function. So let me do that now. All right, now remember what phi is. So phi of y is some constant that right now we won't really care about. See, absolute value of y to the n minus 2, but on the boundary of the ball, so on the sphere of radius r, this becomes c over r to the n minus 2. So on this thing, so, which is nice because it does not depend on y. But now, if we want to use the polar coordinates formula, we do get that. The integral of the ball of phi of y dy then becomes integral from 0 to r, integral over the ball, over the sphere radius r, of this function, which is c over r to the n minus 2, is sigma y. And that should be an epsilon dr. Okay, and the nice thing is, r does not depend on y, so we can pull this out. Okay. So it's integral from 0 to epsilon of c over r to the n minus 2 times integral of 1 of this junk, but integral of 1 of something is just a measure, like area or volume of this thing, which here becomes the surface area of the sphere. And I'll definitely make a video on that, but it turns out there's a nice thing about the surface area of the sphere. It's given precisely by the derivative of the volume of the ball. So it's, in this case, volume of the ball is r to the n times something. So the surface area is n r to the n minus 1 times the volume of the unit ball, which I denote by alpha n. So, in the end, we're left with that this jump equals to c integral from 0 to epsilon of c over r to the n minus 2 times n r to the n minus 1 alpha n. But those three things, they're constants, so let's just put it inside of another constant. So it's c times integral from 0 to epsilon. Now, again, this might blow up, but notice the exponents precisely balance out to give you a nice exponent, which is r, dr. And then, well, this you can anti-differentiate, and you get c epsilon squared over 2 And usually we're scared of letting epsilon go to 0, but now we're super happy. We can let epsilon go to 0 and find out that finally our first term A goes to 0. In other words, the stuff we were scared of blowing up actually doesn't blow up, which is good, which makes this work. Go PD. Alright, so the good thing is the term we thought was gonna blow up does not blow up, but the question is, what about the other term? And what about the f? Where does the f appear in our equation? Well, all this is answered by the next term. So now let's study b. And b, remember, that's integral outside of the ball of our term. Phi of y, Laplacian with respect to x, f of x minus y dy. Okay, and here's what we're gonna do, something that's very exciting in PDE and that makes a lot of PDE work. It's integration by parts. Yay! Okay. Just one thing though, we're integrating with respect to y. Ideally, we would like this Laplacian to depend on y. Turns out it's not too bad to do. So notice, what happens when you take f of x minus y and differentiate this with respect to y twice? Well, by the Chen Lu, if you differentiate once, you get a minus sign. If you differentiate it twice, you get another minus sign. So it becomes minus minus f of, if you want, y, f of, xi. Other words, if you differentiate it with respect to this variable, it's like you differentiate the inside twice, but with two minus signs, and you're left with f of xi, x minus y. And then, all you have to do is sum this over all I, and in fact, on the one side, you get the Laplacian with respect to y, minus y. So Laplacian is just the sum of all the yi derivatives, and the Laplacian with respect to x is just the sum of the xi derivatives. So, in fact, you see that both of them are equal, which tells us it's time to integrate by parts. So, in fact, this equals to some integral over Rn of phi of y, Laplacian with respect to y, of f of x minus y dy. Okay. Alright, now we want to, again, one thing, integral outside. Now we want to integrate by parts. Why? Because, remember, outside of this ball, phi is good. You know, there's no mole or anything, you know, outside there. So in particular, if we took the Laplacian of phi, in this region, we would actually be okay. So that's why, ideally what we'd like to do, we want to take the Laplacian and transfer it back here, which again begs the question of integrating by parts. Okay. And for this, we do need an integration by parts formula. So fact 2, the IBP formula. How do you do it in multiple dimensions? Well, first of all, in one dimension you have the following. So in 1D, this is the analog of, let's say, f times g double prime. Integral from a to b, f g double prime, and again dx or something. That's really the same as, if you integrate by parts, f times g prime from a to b minus integral from a to b of f prime g prime. So, here you have a function and then its derivative, and here we have the product of two derivatives. And the formula I write down in a second is very similar to this. So just watch for this, okay? Alright, so here the analog is the following. Suppose you have a region A and you take f Laplacian of g, again dx if you want. Something that's dx. What you want to do, so again, this is the analog of fg double prime. First of all, you want this fg prime, but before we evaluate it at certain points, now we want to evaluate it on the boundary. So it's equal to the boundary of A of f gradient of g, again, the sigma of x, the surface of A. Okay, so again, here's drawing a picture. This is A, and this is the surface. Okay. And then minus derivative of f times derivative of g, so f prime g prime, which here becomes gradient of f times gradient of g, and to properly multiply them in this case, you get gradient of f dot gradient of g dx. Okay. This is all in good, except this doesn't really make sense. How do you take a derivative on the boundary? And in order for this to make sense, in order to have a derivative on the surface of a function, you have to replace this by what's called the normal derivative. Namely, partial g over partial nabla, or nu, something like that, nu I think, okay, where nu is really the exterior normal to the surface. Namely, it's a vector that always points perpendicular to your boundary. So something like that. So again, where partial g over partial nu is just a gradient dotted by nu. So it's like a directional derivative in the direction of the outward pointing unit normal vector. So let me write that down. It's hard to say. So outward pointing unit normal vector. Try saying that 10,000 times. But then you'll be good at multivariable calculus, hopefully. Okay, great. Now that we have this integration by parts formula, we can actually integrate by parts. So here, again, b, what is it? It's integral over Rn minus b0 epsilon of phi of y derivative of f, Laplacian of f of x minus y dy, and again, this Laplacian with respect to y. Now, integrate this by parts, and just be careful. So here's a cool thing. Our region here is, in fact, Rn minus b0 epsilon. It's like everything without this hole, but the cool thing is the boundary of this set is precisely equal to the boundary of this ball. So the boundary, like the sphere of radius epsilon, is precisely the boundary of this exterior region. So in other words, this becomes boundary sphere of, then you want to integrate this by parts. Again, phi of y, and this time the normal derivative of f of x minus y d sigma y. Okay. Let's call this c because we want to analyze this. And then minus simply the gradient of this times the gradient of that. So minus integral of Rn minus b of 0 epsilon gradient of sigma a gradient of phi dotted with gradient of f of x minus y dy. Gradients with respect to y, and let's call that d. And I think I can promise you there's no other e, so those are the two terms that we'll still need to analyze. Okay, and again, this term, remember phi might blow up, so this is potentially dangerous again, and let us show that no, it's not very dangerous. So let's estimate c. Step 4, study of c, and I'll write down what it is again. So again, to show that it goes to 0, let's estimate it, so that becomes less than or equal to, if you want, what is c? It's the integral over the boundary of just phi times the normal derivative of f. So df over d mu x minus y dy, and we want to use the triangle inequality, so which tells you that you can put the absolute values inside. And as usual, so f, it's smooth, it has compact support, so basically this term doesn't really matter because it's bounded. But let me just quickly show you that. What is df over d mu? It's the gradient dotted with mu, and then you can use Cauchy-Schwarz. Okay. Great video, by the way, if you want to see the proof. So the absolute value of the dot product is less than or equal to the absolute value of, the length of the two. But now, mu, it's a unit normal vector, which means that it has length 1. Again, as in unit, g unit, okay? And the gradient, f, is a bounded function, it's smooth, compact support. So in particular, the gradient itself is bounded. Okay? So in the end, this whole thing is less than or equal to a constant. So this thing becomes less than or equal to a constant times surface integral of phi of y, and remember phi is just a constant times, if you want, phi of y, it's a constant times absolute value of y to the n minus 2, but if absolute value of y equals to epsilon, this becomes c times epsilon to n minus 2 d sigma y. And then again, you can pull this thing out. Again, you pull all the constants out. You get c times epsilon to n minus 2 times integral of 1 of this, which becomes, again, the area of the surface area of the ball, which is c times n epsilon to the n minus 1. Maybe let's write alpha n times n to the epsilon of n minus 1. And just as before, there's this miracle where the exponents precisely balance out so that in the end, you just get a constant times epsilon, which goes to 0. Again, witness how analysis is at play here. So, the term c, so the boundary of the ball, is actually not that bad. It goes to 0, and then we're just left with the other term. All right, and by now you should be a bit worried, because first of all, when will this video ever end? I'm just keeping talking about terms and terms and terms. And moreover, so far, all the terms, they went to 0. So the question is, where in hell do we get, Poisson's equation? Hopefully now in this, I guess, basically last step, I will answer you this question. So step 5, study of D. Okay. And I like to remind you, d is minus the exterior integral, if you want, of the gradient of phi dotted with the gradient, if one with respect to y, of f of x minus y dy. And the cool thing is, once we've integrated by parts once, we can integrate by parts twice. So let's integrate by parts again. Okay, so this gradient goes up, and you're left with integrate by parts. Here, sort of in the reverse order. So integral over the boundary of this, which again becomes the boundary of this ball, of, so the derivative here disappears. So you get f of x minus y. This derivative becomes a normal derivative, d phi over d nu of y, d sigma of y. And then minus minus, so plus the integral over the good region of Laplacian of phi of y times f of x minus y dy. Okay, nothing more than that. But now, perhaps the most exciting part of today's video. Remember, outside of the singularity, phi is actually good. So you can legitimately differentiate phi, outside of the ball. So in particular, there I did it again, okay? You get that the Laplacian of phi in that good region, okay, is actually 0. So this whole thing is 0, and you're just left with one term here, namely the integral over the surface of the ball of the normal derivative of phi times f. And now let's roll up our sleeves, sort of, and calculate actually this normal derivative, because it turns out we can exactly calculate this time. And you'll see another nice thing happens here. So no, normal derivative of phi, that's the gradient of phi dotted with the unit normal vector. And because we're dealing with the ball, we can calculate this unit normal vector. So let's see what this equals to. So first of all here, we have our region. Rn without b of 0 epsilon n. Here's the important thing. Usually when you're on a ball, the unit normal, exterior unit normal vector points this way. But because our region is inside out, so because we're dealing with the outside region here, the unit normal actually points this way. Think of it as forces. I think it's a centripetal force or something. Anyway, it points out inside, which means that we have to have a minus sign, because usually our vectors point outside with a plus sign. But here we have a minus sign. That's the first thing. Second of all, given a point y, in this case, it points to the direction of y, so it's proportional to y. But finally, because we're dealing with a vector of length 1, we have to divide it by the length. So it becomes minus y over absolute value of y, which in this case becomes minus y over epsilon, because we have the surface area of the ball. We have the boundary of b0 epsilon. That's our first ingredient. And now let's also calculate the gradient of phi. That is new on purpose because we need it in a second. All right, so phi of y equals to, usually I don't care about the constants, but here turns out we choose them precisely to make something interesting happen. So let's differentiate this. So gradient with respect to y of phi over n times n minus 2 alpha n. And now let's differentiate this sucker using the chain rule. Okay, so it's something subtle going on here. First of all, let's use the power rule. So n minus 2, sorry, there should be a 2 minus n. 2 minus n, okay, differentiate that, y to the 1 minus n. That's like the power part of it. And now we need to differentiate the absolute value. But remember, derivative of absolute value is the vector divided by absolute value of that vector. And now there's a cancellation party going on. This absolute value of y cancels out with this 1. And then 2 minus n cancels out with n minus 2, except for minus sign, which is also why we chose n minus 2. Okay? So it becomes minus 1 over n alpha n, okay, y to the minus n times y. So it's this big constant times y. And now we have our two pieces of info that we have. We have our unit normal vector, we have our gradient. And so now let's calculate the normal derivative by dotting those two. Okay. So d phi over d nu equals to, okay, so our gradient, so minus 1 over n alpha n, absolute value of y to the n times y, dotted with minus y over epsilon. Okay. Minus y over epsilon. Okay. Now, the minus signs, in case you were worried, they cancel out. And now, we have in fact that y dot y, remember from multivariable calculus, the dot product of a vector with itself is the same as the length squared. So we have 1 over n alpha n, y to the minus n, y squared over epsilon. And now remember that on the sphere of radius epsilon, we get absolute value of y equals to, absolute value of y equals to epsilon. So it's 1 over n alpha n, epsilon to the minus n, epsilon squared over epsilons. So it's a cloud of epsilon appearing, but in the end you have 1 over epsilon, 1 over n alpha n, epsilon to the 1 minus n. This gives us our, d phi over d nu, and now we need to replace it in our formula. So d becomes the following. Basically the grand finale. So d is minus integral over the boundary of the ball, 1 over n alpha n, epsilon to the 1 minus n, f of x minus y d sigma y. Okay. And now, so y lies on the surface of this ball. That's epsilon and that's y. And let's just translate this ball, a little bit. In other words, let's do the change of variables. Okay. Z is x minus y. And all this does, this minus y part, just flips it on the other side of the sphere. So no problem at all. And this x, it just translates it by x units. So in the end, we're left with the ball of radius epsilon and ball of radius epsilon was centered at 0 as x. So in the end, we get ball of radius centered of x and radius epsilon of all this junk. So f of z d sigma z over n alpha n, and then the epsilon of 1 minus n becomes epsilon to the n minus 1. Okay, and here comes the exciting part. The question is, how does this relate to this number? Well, if you think about surface areas, this is actually precisely equal to, if you want, alpha n times n to the epsilon to the n minus 1, but it's precisely equal to the surface area of the ball of radius epsilon. Okay. So in other words, this weird term actually becomes the following: integral over b of x epsilon f of z, I forgot the minus sign, minus f of z d sigma z divided by the measure, if you want, of that ball. And in general, if you have an integral divided by the measure of the set, just like in 1D calculus, it's like the average value. So note, one integral of f over a divided by the measure of a, it's the average integral of f over a. So this whole thing becomes the average integral of b of x epsilon f of z d sigma z. And the question is, let's say you take the integral over this sphere, okay, gives you a certain value. Or in other words, let's say you take the average of f over that sphere and let epsilon go to 0. In other words, suppose that z is very close to x, then that average should actually be very close to f of x. In other words, the average of f around x, if f is very smooth, should be f of x. So in fact, you can show, it's not too bad, you just replace, write the average of f of x. You write the number f of x in terms of an average. So you can actually show that as epsilon goes to 0, this gives you minus f of x. We're basically done, but let me just recap what we did. What the hell did we calculate? Remember, long time ago, we calculated the Laplacian of u. We decompose it into lots of terms, all of which go to 0, except for this one term, which goes to minus f of x, which tells you, in fact, that minus Laplacian of u equals to f of x. So, after lots of analysis and lots of explosions and lots of chalk breaking, we've shown that minus Laplacian of u equals to f of x. So in fact, u, given by the formula, solves Poisson's equation. Alright, thank you for watching. If you like this and more analysis and want to see more math videos in general, please make sure to subscribe to my channel. Thank you very much.